So in this lecture, we'll have a look at what we mean by a discrete random variable and the definition of the probability mass function. So the starting point is that we have a random variable x, which, as we remember, is just a function from the sample space onto the real numbers. The codomain is the real numbers, but the range of x turns out to be very important. Remember, the range of a function is the collection in the codomain that the function can reach. Another way we can say that is that the range of x is the possible values that we can get from the random variable x. So we say that the random variable x is discrete if the range of x is finite or countably infinite. So by finite, we simply mean that the range of x does not contain an infinite number of elements. At this point, it's not crucial that you know the concept countably infinite. Just know that this set 1, 2, 3, 4, which continues indefinitely, is an infinite set, but it's countably infinite. We can sort of count them 1 to 2 to 3 to 4 and so on. While an interval, such as the interval between 0 and 1, containing all real numbers that are between 0 and 1, is uncountably infinite. There is no way of sort of counting them. Starting from 0, you can't say what the next number would be in such a sequence going all the way up to 1. But most importantly, if the range of the random variable x is finite, then the random variable must be what is called a discrete random variable. So if it's the case that x is a discrete random variable, then we remember that this set is an event. This is a subset of the sample space. Since it's an event, it must have a probability, and the probability of this event is denoted like this. Both the event and the probability depends on the value of the real number lowercase x. So just to save on our notation, we typically denote this probability by lowercase f of x. And this function, lowercase f, is then called the probability mass function, which is often abbreviated with PMF. So this function f will have as its domain the real numbers, and since it's a probability, its codomain will be the interval 0, 1. Now, it is common to define the domain of f as the collection of real numbers, even though the random variable x may only take a finite number of values. So for example, if the range of my random variable x is 0, 1, and 2, then we still define f of x for an arbitrary real number x, but we set it to 0 if x does not belong to the range of x. While on the other hand, f of 1, for example, is defined as the probability that x takes the value 1, and so on. So here is a simple example. Let's say my sample space is alpha, beta, just two possible outcomes. Let's say that the probability of alpha is 0.7, which means that the probability of beta is 0.3. And let's just say I define my random variable such that it maps alpha to 0 and it maps beta to 1. We see that the range of x is simply the collection of 0 and 1. Those are the two possible values that x can take after the experiment. This is a finite set, so x is a discrete random variable. For this example, we can see that f of 0 which is the probability that x will take the value 0, that is the same as the probability of the experiment ending up picking alpha, and this will then be 0.7. Similarly, f of 1 is probability that x is equal to 1, which is the probability that the experiment will pick beta, and that must be 0.3. And it's then implicitly understood that f of x is 0 if x is not one of these numbers. If we would like to make a graph of the PMF, we would draw something like this. This is x, this is f of x, and we have 1 here. Then f of 0 is 0.7, so maybe that's around here. We would draw it like this. F of 1 is 0.3, so if we have 1 here, then maybe we have 0.3 here, so we would draw it like that. For all other values of x, the probability mass function is 0, so we could draw that something like this. No matter how the random variable x is defined, as long as it's discrete, its probability mass function must satisfy two conditions. So let's say I have a random variable x, it's discrete, and let's say that it can take the values x1 through xn, where these are just numbers. So the collection of x1 through xn is the range of x. Then x has a probability mass function f, and it must satisfy the following conditions. First of all, f of xi must be greater than or equal to 0 for all I. This only tells us that we cannot have negative probabilities. The second condition says that if I sum f of xi over all possible values that x can take, I must get the number 1. For example, considering the previous example up here, we had two possible outcomes. So x1 was 0 and x2 was 1. The second condition then tells us that the sum, when I go from 1 to 2 f of xi, that's simply f of x1 plus f of x2. This is the sum here. This must be equal to 1. This is simply the claim that x must take a value in its range. It must do so with the probability that's 100%. So in the general case, if x can take n different values, then if I sum these probabilities, I must end up with 1. From these two conditions, we can also conclude that f of xi must be less than or equal to 1. Again, this is natural. Probability can never exceed 1. But we don't have to write it down as a separate condition because it will follow from 1 and 2. So we also discussed the possibility that the range could be countably infinite. In that case, we can denote the range of x as the collection x1, x2, but we do not put a final xn. We just write ... to illustrate that this will go on forever. So we have an infinite range. So when n is infinite, the second condition must then be stated that the sum, when I go from 1, not to n, but to infinity, f of xi, that must be equal to 1.